and we move to the last talk of the session. Okay, so we have Emanuele Berti, and he's going to talk about testing the Kerr paradigm with gravitational waves.
Thank you for the invitation, first of all. Wish I could have been there in person, but these are strange times. Let me start by motivating a little bit what I'm going to discuss today. We all know that black holes are playing a more and more prominent role in modern physics, and here I thought it was amusing to show a diagram of all the Nobel Prizes that have been awarded. You can notice immediately a couple of things, that in the past 20 years or so, many of these Nobel Prizes were awarded for discoveries in astronomy, astrophysics, and cosmology. And over here I have a timeline of recent Nobel Prizes in this field. In particular, you can see that the ones in yellow were awarded for discoveries that had to do with the existence of astrophysical black holes. So through, either theoretical predictions or observation in X-rays or gravitational waves and so on. Now, the key question behind the talk that I'm going to give today is, can we really be certain that these very compact objects that we are observing are indeed the black holes of general relativity? We have no proof of that, but I will argue that we can use especially gravitational waves to get closer to a confirmation of these hypotheses. So first of all, why should we bother considering solutions that are different from Kerr in the first place? The reason is that, as you all know in this audience, there are many good reasons to consider alternatives to general relativity. All of these alternatives to general relativity in general emerge because we have one or more violations of the hypothesis that are behind Lovelock's theorem, which you can think of as a sort of a uniqueness theorem for the Einstein field equations plus possibly a cosmological constant. I don't want to go into this because I don't have the time, but the general idea is that whenever you violate one or more of the hypotheses behind Lovelock's theorem, you end up introducing, in general, additional degrees of freedom that can be scalars, vectors, or tensors. Now, the question is, does these additional degrees of freedom modify black hole solutions and their dynamics in a way that we can potentially test with gravitational waves or not? Now, if you take the simplest of these modifications, suppose that you take one of the old-fashioned scalar tensor theories of gravity, or what is sometimes called the Bergman-Wagoner type, then the answer is no. And the reason is quite simple to understand. If you compute the orbital period derivative for binaries in a scalar tensor theory of gravity of this relatively generic form, what you find is that there is the traditional quadrupolar contribution to the energy loss, and there is also a dipolar contribution, which, however, is proportional to what is called the difference between the sensitivities of the two objects that make up the binary. So you don't have to look at these complicated equations. All that matters is that if you take black holes, the sensitivities of black holes are equal to each other and equal to 1/2 in scalar tensor theories of gravity, and therefore this dipolar emission vanishes identically. Now, there is a hint that these effects may not be observable in this very specific class of theories, but in fact, this very simple argument has been extended to higher post-Newtonian orders by many works that they list down here. It has been shown to be exact in the large mass ratio limit, and it has even been shown to apply in numerical relativity simulations of black hole binaries in scalar tensor theories of gravity. There are ways around this no-go theorem, but they either involve adding matter or adding cosmological boundary conditions, which means that the modifications that you would introduce are very hard to observe using LIGO because they are suppressed basically by the Hubble scale. What I will discuss in this talk is another possibility that the curvature itself may be sourcing the scalar field and therefore producing black hole solutions that are different, the dynamics of black hole binaries that can be different. So there are various reasons for considering curvature corrections to the action. And I will bring up a couple of arguments. The first argument is that you want to systematically explore small corrections. Why small? Because we know from LIGO that the observations are already consistent to a very good degree with general relativity. So we can assume that whatever corrections appear to the Einstein-Hilbert action are going to be small. What do we mean by small? Well, we can do a curvature expansion, and we can look for all possible curvature invariants that are coupled to scalars. This was done in many papers. Here I have these equations from a paper by Cano and others. And what you get in general is that you will have corrections that depend on different powers of the curvature. There is a quadratic curvature invariant that is known as the Gauss-Bonnet invariant. Then you can have Riemann times the adjoint of Riemann, and then you will get dynamical Chern Simons corrections. And then you can have higher order corrections in the curvature. What matters is that if you want to include higher order corrections in curvature, necessarily the coupling constants that appear here in order to make the action dimensionless will have to appear with a certain scale. Now, if you believe that this scale has to be the Planck scale, forget about testing this in astrophysics. But we're going to be agnostic, and I will assume that this scale can potentially be of the same size as, say, the horizon scale of astrophysical black holes. And I will ask, can we test these corrections if they appear at astrophysically relevant energy scales? Let me also mention that you don't have to couple these curvature invariants necessarily to a scalar field. You can also consider corrections that do not introduce additional degrees of freedom. This was done in this work, for example, among others. And then you can get additional corrections that are going to be quadratic in these curvature invariants that are themselves quadratic in the curvature. So these corrections, you can expect them to be very small if your curvatures are not particularly large. A second motivation to consider the class of theories that I will discuss a little more in detail in this talk is the same motivation that basically David Langlois was mentioning earlier. You can look at generic scalar tensor theories, more general than the Bergman-Wagoner class that I was considering before. And in this case, what you can realize is that if you single out Hordensky theories of gravity, which are less general than the Dost theories that David was discussing this morning, under certain assumptions for decoupling functions, you can see that the Einstein scalar Gauss-Bonnet gravity theory that I was discussing before appears as a limit of these generic equations, these generic actions for scalar tensor theories of gravity that are quadratic in the curvature. So these are two different ways that you can see the potential appearance of these terms. What I'm interested in is understanding whether these class of theories can give you black hole solutions and black hole dynamics that are different from GR. And the answer is yes. A simple argument to see why this is the case is that you can take, for example, the equation for the scalar field in one of these theories. You can multiply that equation by the FD phi, where I remind you that f is the function through which you couple the Gauss-Bonnet invariant to the scalar field. So you multiply by the FD phi, you integrate by parts, you use the divergence theorem, and you see that on the right-hand side, you have a boundary term that you can show has to vanish. And on the left-hand side, you have something that can, a sum of two terms, that can only vanish separately if this condition applies. So this particular combination of the second derivative of f multiplied by the Gauss-Bonnet invariant is relevant effectively because it acts as a mass term in the scalar wave equation. You can see it in a different way if you linearize the scalar field equation, and then you see that the same combination evaluated at the background scalar field appears as a mass term. So what you can have is that depending on the sign of this object here, you can induce a tachyonic instability and therefore produce the analog of what Damour and Esposito Ferez studied in the 90s, where you don't need to couple to matter. All you need is a non-zero background curvature. And depending on the sign of this quantity or on the sign of the curvature itself, you can have spontaneous scalarization whenever your mass term becomes tachyonic. I will not discuss this in detail again because it was discussed in Thomas Sotiriou's talk. But what is interesting is that in the past few years, people have been studying this class of theories. They have shown that these scalarized solutions exist. They can be stable. They can be sensibly different from GR. They can have an interesting phenomenology for LIGO when the scalarization is induced by the spin, which means that this G term now becomes negative when the spin is large enough. And people have computed dipolar radiation in these theories. You have non-trivial scalar field profiles, you have scalar charges, therefore you have dipolar radiation for black hole binaries. We have been working on developing an effective one-body approach to these post-Newtonian calculations. And even more interestingly, people have been computing waveforms for binary black hole mergers in these theories, either using a weak coupling approximation or in the full theory. So the bottom line of this first part of my talk is there are theories of gravity which are potentially testable with gravitational wave interferometers when we observe binary black holes, because in these theories of gravity, you can have dipolar radiation and non-trivial black hole solutions. Now, the question is, what kind of tests can we get from observations of inspiraling black holes or black hole mergers on these classes of theories of gravity? And I will discuss these two problems in the next two parts of the talk. First of all, I will show you that the tests that you can get from the inspiral phase of black hole binary coalescences are, these bounds are going to get better over time. And the amount by which they're going to get better depends both on which gravitational wave detectors are going to be funded and on uncertainties in the astrophysical populations. In the last part of my talk, I will discuss the constraints that you can get from the ring down. And I will present arguments that are similar to the ones that David was discussing this morning. So let me start from the inspiral. I would like to be able to place bounds on generic modifications to general relativity. One way that we can do this is by saying, well, I know that the Fourier transform of the gravitational wave amplitude is going to have a certain amplitude in general relativity and a certain phase. And quite generically, I can say, if my theory of gravity is not general relativity, then there are going to be corrections to the amplitude, which will scale with a certain power of the orbital velocity of the binary. And there will be corrections to the phasing that will also scale with a certain power of the orbital velocity of the binary. Let me call the power B. Now, I can collect LIGO data, which is what you see down here, and I can ask, are the coefficients in the phasing of the gravitational waves, which are the quantities that I can measure better, consistent with the GR hypothesis? If they are, all of these violin plots should be consistent with 0. And indeed, you can see that they are, with certain errors that are relatively large. They are shrinking as we observe more and more events. But you can see this as tests that different modifications to GR, which appear at different post-Newtonian orders, have to be in some sense small. Now the question is, how are the errors on these violin plots going to shrink as my gravitational wave detectors get better and better? As I said before, this depends on which detectors are going to be operational in the future. And we did a pretty comprehensive study of this problem together with Scott Perkins, a student of Nico Younes, and Nico. What we assumed is 3 different scenarios. One of these scenarios you can see as pessimistic. It's a scenario in which neither Cosmic Explorer nor the Einstein telescope are going to be funded in the next 30 years or so. And all we are going to have are technological improvements in the existing LIGO facilities, in particular in Hanford, Livingston, the Virgo detectors, and then, as you probably know, there's a LIGO facility in construction in India, Indigo, and the Japanese detector has already started taking data. So we assume that only these detectors are going to be upgraded, and at some point, around 2035 or so, we will also have LISA. In these two other scenarios, we assume that there's going to be at least one third-generation detector, for example, Cosmic Explorer, or two of them, one in the US and one in Europe, say, Cosmic Explorer and the Einstein Telescope. So under these different scenarios, you can ask, how many events am I going to observe over time? So we are here, and this is, you know, some date in the future, 2025, 30, 35. At this point, you turn on LISA, and you have LISA for about 10 years, and so on. So on the left, what you see is the number of sources that we expect to observe only with the ground-based detectors. And as you can see, this number of sources will go up from hundreds or thousands now to something like millions of sources, depending on the astrophysical models that you have, when you have several detectors. The other thing that is going to change drastically is that as you have more and more detectors, and in particular, if you have third-generation detectors, you can have larger signal-to-noise ratios. A large signal-to-noise ratio means that each of these events is going to be more constraining. What you see on the right is that when you look at massive black hole binaries observed by LISA or multi-band events that are going to be seen both by LISA and LIGO, you will similarly see that your signal-to-noise ratios and your number of events is going to improve, but we don't expect to see more than tens or maybe, in the most optimistic scenario, thousands of events, massive black hole merger events. So you are going to lose in terms of number of events, but you're going to win in terms of the signal-to-noise ratio. Many of these events are going to have larger signal-to-noise. So the question is, what is going to be more constraining? Is it going to be the very many not so loud events that we see on the ground, or the relatively few but very loud events that we see in space? And the answer to that question depends on what you're looking at. Now, there's too much information in this plot, but each of these panels corresponds to one of these different post-Newtonian corrections. This parameter B can be mapped to the post-Newtonian order of your modification. For example, a dipolar radiation term would appear as a -1 pn correction, which means that B is equal to -7 here. And as you can see, for dipolar radiation effects, the bounds are going to get better and better over time. You see, these are the bounds that you can get from ground-based detectors. At some point, you're going to have bounds also from LISA observations of massive black holes or multi-band binaries, and those are not going to be as competitive. But basically, the answer is just go and look at the paper, because depending on what modification of gravity you're interested in, different sources are going to be more or less constraining. And you can see here a little summary of the main findings of our paper. What we find is that massive black holes are better than stellar object binaries, stellar origin binaries and negative post-Newtonian orders. Terrestrial detectors do better at positive post-Newtonian orders, and so on and so forth. In fact, you can find very simple scalings that tell you that the constraints that you get depend not only on the signal-to-noise ratio, but also on the Chern mass of the source. And this is why space-based observations of massive black holes in some cases do better than terrestrial observations at negative post-Newtonian orders. The other thing that you can understand also is that sometimes very few loud sources are going to give you all of the bound, and adding multiple sources is not going to help you very much. And this is particularly true when you look at negative post-Newtonian order effects. Be it as it may, once you have these generic constraints on post-Newtonian terms, what you want to do is map them into theories. And you can do it for several classes of theories of gravity. I'm in particular interested in these Einstein scalar Gauss-Bonnet bounds that appear as dipolar corrections. And so I'm going to show you what happens for this particular class of theories. What you see here is that this is the same plot that I've shown you before for a generic modification to the dipolar emission term. But when you want to map the dipolar emission to Gauss-Bonnet gravity, you basically have a Jacobian that tells you that you need to map this dipolar correction to the specific kind of modification that appears in Einstein scalar Gauss-Bonnet gravity. And what you see is that terrestrial detectors, in fact, typically tend to do better than multi-band detections or detections of massive black holes for this particular class of theories, which doesn't mean that this is going to be true in general, but it is definitely true in this class of theories. Okay, I could say more. I will just leave you with this table at this point, and I will turn to discussing. So you can look at the breakdown for all different classes of theories of gravity in that paper, but I will not discuss it anymore. The second thing that I want to discuss in this talk is, can we parametrize ring-down deviations in generic modified theories of gravity? So in this part of the talk, I will discuss 2 or 3 papers that we wrote together with my postdoc Ryan McManus, Vitor Cardoso, and others. The general idea is similar to what David was discussing this morning. So suppose that we start from, for simplicity, a non-rotating black hole in general relativity. We know that the perturbation equations in the 2 sectors, axial and polar, are basically Schrödinger-like wave equations. Notice that I'm factorizing the potential by putting a factor of f, which is basically the redshift factor in front of the potential itself here, but these are the Regge-Wheeler and Zerilli equations that many of you are familiar with. In GR, a very special result is that the spectra for the even and odd potentials are the same. And you can also write scalar and electromagnetic perturbations in the same way with potentials that have the same form as the gravitational potential, except that you have S, the spin of the field here. So now what I want to understand is, suppose I have a generic modification to my gravitational theory. Instead of Einstein's theory, I have a different one. And instead of computing the perturbation potentials on a theory-by-theory basis, I want to parametrize. So let me assume that the potentials for the even and odd perturbations are going to be corrections that will be small in some sense. Each of these constants alpha could depend on coupling parameters in your modified theory of gravity. I will just assume that the corrections appear as a series of inverse powers in 1 over r, in the, if you like, parametrized post-Newtonian spirit. Well, if I consider that each of these corrections is going to be small, because alpha itself is small, then I can do perturbation theory, and I can compute corrections to the quasi-normal mode frequencies in GR as a series of powers, where these coefficients D and E will be universal, and alpha and beta, the constants that appear in this expansion, will be assigned whenever you give me whatever your favorite theory is. So suppose that you give me a theory like Einstein scalar Gauss-Bonnet, then you will specify the values of alpha. I can compute E and D once and for all. Once you tell me what your favorite theory is, I can tell you what the corrections to the frequencies are going to be. In fact, you can derive generic criteria for these corrections to be small, which are conditions on the coefficients alpha and beta. And also, you can compute these coefficients E and D and whatever I call them generically. So you compute them once and for all. You can verify that they're going to decay for large values of the power law J here in a way that can be predicted analytically. And then what is interesting is that by doing this very general calculation, you can ask questions related to the specific theories. For example, I told you that isospectrality is a very general property in general relativity. You can ask, if you give me modifications to GR, what are the conditions on the even and odd perturbations of the potentials that need to be satisfied in order for modified theory of gravity to preserve isospectrality. And you can write these conditions analytically once and for all. There are conditions between the coefficients alpha 0, alpha 1, alpha 2, and so on that need to be satisfied order by order. And you can see that isospectrality is a very special property. There is only a very limited class of modifications that you can imagine that will preserve isospectrality. But more interestingly, if you give me modifications to GR like the ones that I was discussing before, you can map them to your modified coefficients. So, for example, you can take the effective field theory modifications that I was discussing in one of the first slides, and you can say, can I compute in this very general approach the modifications to the frequencies, and do they map to specific calculations in that particular class of theories that have been done before? The calculation for these quadratic theories had been done in a paper by Vitor with Alessandra Bonanno, Senatore, and others. And they found certain corrections to the frequencies. What we did was we took we read out from their paper what the correction had to be. This correction, as you can see, appears as a 1 over r to the 10 power. You expect it to be very small. All you need to do to apply our formalism is to read the alpha 10 coefficient. You plug it into the generic calculations of the E's that we have performed, and you find corrections to the frequencies that are in excellent agreement with the numerical integrations in this particular class of theories. Now, the power of this formalism is that you can do it for whatever theory you give me. For example, you can imagine that Einstein-Maxwell is a modification to general relativity. And in this case, the perturbation parameter is the charge of the black hole. So you can write down the Reisner-Nordstrom solution. You can think of the charge now as your perturbative parameter. You can perform a change of variables that brings the wave equation in the canonical form that we want. And then, as you can see, you have a bunch of coefficients here that appear as inverse powers of 1 over r. These will be coefficients that you can read out. And then you can ask, in the case of Reisner-Nordstrom, I can compute these frequencies exactly. Does my perturbative formalism reproduce the Reisner-Nordstrom frequencies that are very well known? And the answer is yes, as long as the perturbative parameter is small enough. Of course, you're doing perturbation theory. When your perturbative parameter becomes of order 0.5, your corrections start being of order 10% or so, but the agreement is still pretty good. Another example. You can take the scalar wave equation and you can imagine that now your perturbation on top of the Schwarzschild background is induced by rotation. Now, this is not even a modified theory of gravity, but you can treat it within the same formalism. You can compute your frequencies at linear order in rotation, and you can look for the disagreement between rotational corrections and perturbation theory at linear order. And you can find that these corrections become relatively large when rotation becomes large. Okay, now, if you think of David Langlois' talk this morning, the case that I consider so far is not realistic enough. And the reason is that if you consider a scalar tensor theory of gravity in general, your scalar and tensor degrees of freedom are going to be coupled. So what you would really like to have is a more complete formalism in which at least you want to allow for coupling between the scalar and the gravitational degrees of freedom. So in the second paper in the series, the one here, we did exactly that. We said, suppose that you have a vector of perturbation variables. In the scalar tensor example, this vector will contain the scalar degree of freedom, the gravitational axial degree of freedom, and the gravitational polar degree of freedom. And your perturbations will satisfy a matrix equation where these V's are Bij objects, they belong to a matrix, and the off-diagonal terms will couple scalar to axial gravitational perturbations and possibly scalar to axial polar perturbations. So in general, you can generalize the perturbative approach I was discussing before by turning these objects into tensors, if you like, matrix valued objects, Aij, alpha ij. Now, kappa will be the perturbation order, and ij will tell you whether the scalar degree of freedom couples to the axial or the scalar couples to the polar, and so on and so forth. Now, you can understand by simple arguments that in general, if your background spectra are non-degenerate, which they are not in GR, remember, because we have isospectrality, but let me assume for a moment that they are, these couplings will introduce quadratic corrections because that's how matrices work. You need to multiply to get the eigenvalues, the off-diagonal terms, and those will give you corrections that are quadratic in alpha. So if you want to allow for coupling, you need to go to quadratic order. And this is exactly what we did in this paper. We introduced quadratic corrections, and we computed all of these objects here, which are the quadratic generalization of the matrices that I called D and E. And we computed them once and for all. You don't have to do this work anymore. We have done it for you, and now we know what these corrections are in general. Now, however, as I told you earlier, in general relativity, the axial and the polar spectra are degenerate. So you need to worry about what happens when you have spectra that are degenerate. And the argument is quite simple. Suppose that you take two spectra that are degenerate. You can simply diagonalize them by introducing linear combinations of the variables phi1 and phi2. And what you see immediately is that if your spectra were originally degenerate, then the corrections must be linear now in alpha, not quadratic. So in the case of interest to us, general relativity, the corrections that appear because of couplings between the axial and polar perturbations are going to appear at linear order. However, we know from quantum mechanics how to deal with degenerate perturbation theory. We can do exactly that, and we can compute corrections to the spectra in this degenerate case. So let me give you examples now of this general perturbation theory applied to cases where your background spectra are degenerate or not. One case in which the spectra are non-degenerate is dynamical Chern Simons gravity. In this case, perturbations had already been computed. If you take the axial perturbations of a black hole in dynamical Chern Simons gravity and the scalar perturbations, the two background spectra are non-degenerate. I can apply non-degenerate perturbation theory to this case. The calculation has been done in the specific theories. I only need to read out the coefficients, plug them into my formalism, and what I find, not surprisingly, is that as long as the coupling between the scalar field and the Chern Simons term is small, my results in the generic formalism are in very good agreement with the results of the specific calculation in this class of theories. A second example that we considered is similar to what David was talking about this morning. You can take Kordensky theories of gravity, scalar-led perturbations, apply the formalism, you find excellent agreement in this case between the perturbative formalism and the specific theory. A third case are odd and even gravitational couplings in the effective field theory that I was describing before. Here, the background problem is degenerate because in GR, the axial and polar spectra are degenerate, but you can compute the corrections, and what you find is that you get decent agreement when the perturbation parameter is small once again. So to summarize, you can introduce generic modifications to general relativity as long as these modifications introduce small changes to the GR potentials. You can apply this general formalism that we introduced to compute generic modification to the gravitational wave spectra. And we demonstrated by looking at specific examples that as long as your perturbation parameter is small, the generic formalism gives you good predictions. There are cases that the formalism obviously doesn't cover. One case is the one that David Langlois was discussing this morning, because in that class of theories, you can't even write down the perturbation equations in a Schrödinger form. So we will have to come up with a generalization of this parametrization that allows us to cover the theories that David was discussing this morning. The other obvious case that we cannot deal with is the case of rotation, because I started from a non-rotating background. In fact, the case of rotation is going to be very difficult in general, and it has been discussed in very specific cases. How much time do I have, Paolo? Am I already over time?
I think you still have a few more minutes.
Okay, good, thank you. So let me say that the rotating case is particularly complicated because whenever you are in a modified theory of gravity, you lose all of the special properties that make perturbation equations in Kerr separable. So the only thing that you can really do when you consider rotating black holes in modified gravity is generically write down the equations in a small rotation expansion, small spin expansion. This has been done in these papers by Kano and others, and they came up with a very clever way of looking at scalar perturbations of rotating black holes. What they did is a lot of work. They wrote down the background up to order 14 in rotation. Why did they have to go to such high order in rotation? Because the black holes that we observe in LIGO have a spin of about 0.7. So if you ask for an accuracy of order 1% or better in the GR frequencies, it turns out that you had to push your perturbation expansion to very high order in spin if you want to reproduce even only the GR part. So they have done precisely that, and then they computed the scalar frequencies of scalar perturbations on top of these black hole solutions by using a lot of tricks, basically using all of the knowledge that we have of spin-weighted spheroidal harmonics in the GR background, and then looking at the boundary conditions, realizing that you have superradiance, and there's all sorts of things that they have taken into account. Let me also point out that there was a recent paper by Leonardo Gualtieri and Lorenzo Pierini who did part of the work at linear order for Einstein scalar Gauss-Bonnet gravity, linear order in spin. Now, okay, this is all well and good, but suppose that we observe a deviation from the expected frequency in general relativity. Can we learn something about modified theories of gravity if we see that the frequencies measured by LIGO or Einstein telescope or Cosmic Explorer or LISA do not match the frequencies in general relativity? So this is a pure data analysis question. I only have 2 slides on this. Let me just explain the general idea. Suppose that you observe Q sources, okay? So say 10 events, okay? Q is N is the number of sources that you observe. So I goes from 1 to N, where N is the total number of sources. And for each source, you observe a certain number of quasi-normal modes Q. What you can say is, if I am not in general relativity, well, suppose that I am in general relativity first, so that these corrections gamma all vanish. I can write down the frequencies in general relativity as a power series expansion in the spin. If my theory is not general relativity, at each order in this expansion in the spin, I will also have corrections that come from the non-GR effects. So you can ask, suppose that I measure the frequencies and the damping times of my quasi-normal modes. How many parameters will appear in this small spin expansion of the quasi-normal mode frequencies? Well, I'm going to have in general d+1 parameters that appear from the spin expansion for each of the frequencies, and I have Q frequencies. So in total, the number of parameters that I want to measure is pretty large. Suppose that I want to keep d = 4 because I want to match the frequencies in GR to a decent accuracy, then the minimum number of parameters that I'm going to have is going to be 2 × 5 equal 10 times the number of frequencies that I observe. So suppose that I observe only one, I still have 10 parameters. Now, this may seem hopeless, but it is not hopeless, because in practice, I'm going to observe many sources. We have already observed 50 of them. And if there is one modified theory of gravity that is the true theory of gravity, then I can say, I will just observe many events, and then I will win because I'm observing many events. How many events do I need to constrain the parameters? Well, if my measurements are perfect, I only need a number of observations which is larger than d plus 1. So by observing many sources, in principle, I can constrain all of these parameters, in principle. In practice, I will be limited by measurement accuracies. So in this paper with Andrea Maselli, we did that calculation. I will not bore you with the details. You can ask me about it if you want to learn more. But basically, we found that not all of the parameters are measurable. This depends on the signal-to-noise ratio of the sources, and it depends on which overtones you are looking at in the ringdown signal and so on. But you can place pretty decent constraints with a detector like the Einstein telescope, and you can hopefully set bounds on these modifications of gravity. In fact, this idea has already been used by the LIGO collaboration. Carullo has written a short author-less paper, and I know that people in the LIGO collaboration are now implementing this idea to get better ring-down constraints on modified theories of gravity. I will leave you with this slide with take-home messages, and I'll stop talking and I will take some questions. Sorry if I ran over time.
Thank you. Thank you very much, Emanuele. So now it's time for questions. I don't see any.
Either everything was very clear or everything was completely incomprehensible.
It was very clear. Okay, now there is a question by Chen. Please go ahead.
Thank you.
Oh, yes, thank you for the very nice talk. So in your parameterized approach, I'm wondering whether this approach can be used to test, for example, there's a correspondence between the iconal quasi-normal modes and photon ring. Yes. Because in your case, you directly parameterize the massive potential, and it doesn't really parameterize the metric itself. So can you comment on this?
Yeah, that's a very good question. So our parametrized approach, if you like, acts directly on the perturbed field equations. So in a way, the iconal correspondence between the quasi-normal modes and the metric that you're talking about is less powerful than this approach because it has been shown that there are theories of gravity in which the iconal approximation does not apply. For example, if you take Einstein scalar Gauss-Bonnet, the modification of the frequencies can be computed exactly. And you can also look at the iconal approximation, and you will see that the corrections to the frequencies that come from the iconal approximation alone become increasingly inaccurate when the coupling between the metric and the scalar field grows. Basically, this is because you don't have the equivalence principle anymore, and therefore the particles in your true theory do not follow geodesics in the absence of the scalar field. So if you like, this approach is more powerful in a way, but you cannot map it to the geodesic correspondence unless you can write down the field equations.
Yes.
So if you have a theory and you can write down the field equations, then from the field equations, you can read out the coefficients alpha and beta in our parametrization. And then you can go back and see whether the correction to the frequencies deviate from the iconal predictions. You see?
Yeah.
The disadvantage is that the perturbation approach that we have only applies on a non-rotating background. And this is the reason why we wrote that paper with Kostas Lampedakis some years ago, where we were trying to abuse the iconal approximation for rotating backgrounds. Because in the case of rotating backgrounds, we do not have calculations to guide us. Everything is much more complicated.
Yeah. Okay, thank you.
Thanks.
Sorry, can I just ask you said that which theory it's known not to have this iconal approximation? Can you repeat again? I just didn't hear it.
Yes. In Einstein-Dilaton Gauss-Bonnet, that was the first case that in which
so it's just phi multiplied by Gauss-Bonnet, right?
E to the phi, Einstein
E to the phi, okay.
That was the first class of theories, I think, in which people computed both the axial and the polar quasi-normal modes. Now, in the case of the axial modes, everything is simpler because there is no coupling in general, unless you introduce parity violating terms like RR tilde. There is no coupling between the scalar and the axial perturbations. Okay.
Basically, it's just pure graviton, right?
Yeah, yeah. But so you need to look at the polar sector in the case of Einstein-Dilaton or Einstein-Scalar Gauss-Bonnet. And when people for the first time did the calculation of the quasi-normal modes in the polar sector, they realized that if you take the iconal approximation, as the coupling between the scalar and the Gauss-Bonnet invariant increases, the deviation between the frequencies that you compute and the iconal approximation also increases, as you would expect. But there were also previous examples in which people consider higher dimensional theories, and they showed that the iconal approximation doesn't apply. These are papers by Konoplia and Stuklik. But they were not relevant for gravitational wave astronomy because they were in higher dimensions. The first case in 4 dimensions was, as far as I know, this Einstein-Dilaton Gauss-Bonnet calculation.
Okay, thank you.
Valerie?
Yes. The signal is not only the set of frequencies, but also a set of amplitudes and phases, right?
Yes.
Can you do similar thing with, systematic perturbation theory to figure out the deviations from amplitudes and phases in this case?
So this is very complicated to do in practice. The reason is that in perturbation theory, even in GR, you can only predict the frequencies. To predict the amplitudes, you have to perform a full numerical relativity simulation of the merger. Now, I briefly discussed earlier that in Einstein scalar Gauss-Bonnet theories now, we have numerical relativity simulations that were done in 2 different ways. People like Masha Okunkova, Helby Witek, and others have computed the waveforms in the small coupling approximation. In that case, you cannot really predict the amplitudes because you are assuming that the coupling between the scalar and the gravitational degrees of freedom is small to begin with. So you are linearizing in the coupling, and you're assuming that you have a GR background, and then you feed that GR background into the scalar field to compute the scalar waves.
Yes.
But more recently, there was quite impressive progress. I think it's quite impressive because for a very long time, people thought the simulations could not be done at all because there is no proof of well-posedness. But now, Will East, Justin Ripley, Franz Pretorius, and company managed to simulate collapse and head-on collisions of black holes in the generic Einstein scalar Gauss-Bonnet theories that I was discussing before, at least when the coupling is not too large, but without truncating the field equations. So now we have some hope that in these modified theories of gravity, you can use numerical simulations as a guide to predict the amplitude of the ring down modes that you will observe. But it's early days. They only did one head-on simulation of black hole collisions in Einstein scalar Gauss-Bonnet, which is not the astrophysical case yet. They have some simulations of in-spiral. In fact, I talk regularly with Justin, but it's much harder to get the full in-spiral in the full theory.
Okay. Okay. So but if the coupling is small, then you probably can do the perturbation theory systematically in arbitrary, I mean, parametrize, if you like, in a similar fashion as you did for the frequencies. You can also probably parametrize the corrections for the small, if they are small.
Yes, the problem is that measuring the amplitudes is very hard, even in GR. And the calculation that you have in mind was done in GR using toy problems, like you take a particle and you dump it into a black hole. In that case, you can compute the excitation amplitudes of the quasi-normal modes in GR exactly, because you can solve for the Green's function. However, if you're looking at a merger of comparable mass black holes, those linearized theory calculations, you're not guaranteed that they're going to apply, even in GR. So in principle, yes, you can solve. In fact, this has been done already. You can take a particle and dump it into a black hole in Einstein dilaton Gauss-Bonnet. And then you can solve the perturbation equations and get the full waveform for the particle falling into the black hole. But this case is too idealized to be applied to gravitational wave data analysis, where you have mergers of black holes that can have comparable masses. You are right, it can be done. But if you want the amplitude calculations to be relevant for gravitational wave data analysis, you need to do full NR.
Okay, but I don't quite understand. Isn't it linear analysis anyway, if when you're talking about the ring down frequencies?
Yes, it is a linear analysis, but the amplitudes of the perturbations can only be determined if you know the initial data that generate your
Yes, I understand.
Kerr black hole.
Right.
And in a merger of comparable mass black holes, those initial data, you can only get them from a numerical relativity simulation.
Yeah, I understand, but you can do that in general relativity and then probably do perturbation theory about general relativity.
Oh, now I see. Okay, then that's an interesting, yes. So what you're proposing is you take the GR background and you use numerical simulations in GR to get the mode amplitude in GR, and
Right.
then you feed
and phase as well. Yes,
that's interesting. Yes, I haven't thought about this. Yes. Yes.
Okay. Very good. Any other question for Emanuele? Okay, if not, so thanks Emanuele, and thanks to all the speakers of this session.